Let's look at, sorry, I'm going to turn this a little bit so that I can sit properly here. Let's look at this problem. And the book that this comes from, I know that chapter 15 is work and energy. So I would look at this problem and think I could solve it with work and energy. First, I'm going to go back to chapter 14 of this book. Doesn't matter the chapter, but the F equals ma. I can solve this with F equals ma, right? I'm going to need to know the two components of the force. 15-pound force. This one here is 15 cosine 20. This one's 15 sine 20, right? I've got weight acting on it, 30 pounds, and that has two components. The motion is going to occur in this direction here, right? So the 20 degrees is here. It's easy to see in this problem. This one's going to be W cosine 20 or 30 cosine 20 pounds. And this one up here is going to be 30 sine 20 pounds. There's another force acting on it, and that's the normal force. And statics has its place, right? If we needed that normal force, we would sum forces. And if I want to put a subscript, I'll put in a coordinate system like that. And in that direction, there is no motion, right? The motion is in the x direction now that I've rotated the xy coordinate system. And so we would have n going up. Those sum of forces equal to 0, statics. And I'll go up and to the left, positive. And so I have n, and then minus 30 cosine 20, that component right there, that arrow. And then I'd have minus also 15 sine 20. And I know everything about that is 30 pounds. That's 15 pounds equals 0. And I could solve for n if we needed to know n. Sometimes when we do this problem, we need to know n because we have a frictional force opposing motion, and that's a function of what that n value is. But in this problem, it says it's a smooth inclined surface. It tells us that there is no friction, and so that's equal to 0. We don't even need to calculate n. Just pointing out that it's still there. And so whenever I use F equals ma, and we'll see solutions in textbooks and other online videos, and sometimes I'll even do what I'm about to say and then realize I probably didn't need to. But whenever I use F equals ma, then on the left, and you could put sum in front of that, sum of forces equals ma. This comes from my free body diagram. Which I've got drawn here on top of the given diagram. I think it's pretty clear. Just double checking the recording screen. And then ma is the kinetic energy. or the kinetic diagram. Sometimes called the mass acceleration diagram. Mass acceleration diagram. I'll always draw my mass acceleration diagram or my kinetic diagram. Some of the forces is going to come from this, and that equals, and I've kind of used up some of my space talking about the normal force here, but that equals this guy. And then I have to draw MA. Do we think it's going to accelerate up? Or accelerate down? I have to make a decision here, and I draw my arrow. I'm going to draw it in that direction and label it MA. So disregard this stuff now. Right, that's my kinetic diagram. That's important. I don't care. I try and get that arrow correct, but I always draw it because that's going to be my positive direction here. Right. Once I draw that arrow, then I will write positive. It's coming from looking at that, thinking about which way to draw that arrow. I would never go the other way, right? So if I had gone like this, let me use a different color. If I had gone like this, MA, then I would have gone sum of forces equals MA, and I would go down. And then if I'm solving for A, like I am in this problem, if it's positive, then it is down. If it's negative, then it is up. But as I go through all my forces, I'm going to be looking at the arrows and evaluating them based on that direction. I'll go back to red. I think it's a little bit easier to see, but I think they're both fine. So sum of forces equals MA from my free body diagram and my kinetic diagram. I'm not going to deal with that. I'm going to go up and to the right positive. I got 15 cosine 20 going up and to the right. And then I have minus 30 sine 20 down and to the left. And that's all the forces. The normal force is perpendicular to that direction, so it has no effect. And that is equal to the mass of my object, my particle in this case, times the acceleration. And so my acceleration, let me just keep going with that. 15 cosine 20 is 14.095 minus and 30 sine 20, 30, moving my calculator, times 20 sine equals minus 10.26. And it becomes a positive value. So I'll add 14.1, I get 3.84. That's my mass times my acceleration is a positive 3.84. It's in pounds, right? 15 pounds, cosine 20, no dimensions. 30 pounds, sine 20, no dimensions. It's in pounds. My acceleration is equal to 3.84 pounds. And the mass, right? I think I'm going to have to make 2 videos. mass, I want to do this off to the side. Normally, I would just put it in here, right? I would put in 30 pounds divided by 32.2 feet per second squared. I'll just do it this way. I was going to talk about it a little bit, but I'll just do it this way. That equals, in terms of analyzing the units, I'm taking pounds and I'm dividing by a fraction. That number, 30 over 32.2, that has units of pound second squared per foot, right? Because the denominator has a denominator, so we flip that over, and the second squared come to the top, and I get pound second squared, and the foot stays in the bottom. That's what we call a slug. So if we're given a problem and it says slugs, we know that it's pound second squared per foot. We can put it in here, and now when I simplify this, I'll put feet over pound second squared in the numerator, and the pounds cancel out, and I'm left with feet per second squared. Should always work out. I'll get an acceleration, and that is going to be a little bit more than 3.84. I still have it on my calculator, so I will divide that. Check on my screen here. 3.84 divided by open parentheses 30 divided by 32.2 close parentheses. It's less than 1, so it's going to make it a little bit more. 4.12 feet per second squared. Now that I know the acceleration, right? Is this a function of time? Is it a function of position? That's position. Time, is it a function of velocity? All those are possibilities, but it's not. No, it's a constant, right? So we can use our constant acceleration equations. And in that direction, the acceleration is up and to the right, 20 degrees. The acceleration is constant, and I have s, and I am looking for the final velocity. How fast will that be going? So s equals s0 plus v0t plus 1/2 at squared. Well, I got time in that, and I don't have final velocity. V equals v0 plus at. All right, I've got my final velocity. It's a function of time. I could probably figure out time in some way. But the question doesn't ask about the time. It doesn't give the time. Maybe there's a better way. So v final squared equals v initial squared plus 2as. All right, I know my acceleration. I know my displacement, s. I know my initial velocity, yep, 2 feet per second. And I want to get my final velocity. So let's try that one. So I got 2 feet per second. And I'm going to square that. I'm going to add to that 2 times the acceleration, 4.12 feet per second squared, times 1 foot. How far is it moved up? 1 foot. And we see that we're going to have feet squared per second squared as the first term. and we're going to have feet squared per second squared as the second term. Probably do this math in my head. 12.24 feet squared per second squared. And V2 is the square root of that. So again, since I already have a number on my calculator, I'll go times 2. That gives me my 8.24. I'll add 4, and I'll take the square root of it, and I get 3.499. 3.499 feet per second once I took the square root. And so, right, V2 equals 3.5 feet per second. And that's the problem with F equals MA.